In this video, we're going to discuss vectors in Rn. So this chapter and the next few chapters will discuss vector spaces and linear transformation, which form the main object of study in linear algebra. So in most applications, when we apply linear algebra to a problem, it boils down to understanding what the underlying vector space is and the appropriate linear transformations for the problems are. And so in this section, we're going to look at vectors in Rn as a way to work with vectors that are familiar to us computationally. And then in the next section, we'll look at more general vector spaces. Okay, so this fancy looking R just denotes the set of real numbers that we're familiar with, and the number that goes with it. So here R2, essentially just the dimension of the vector space, of the real vector space we're working with, right? So here R2 means two-dimensional space, which is just the plane geometrically. Typically in physics or engineering, when you introduce vectors, they're represented geometrically as directed line segments that have a magnitude, which represents the length of the vector, and a direction. Right, so typically a geometric vector looks something like this, right, where it's like an arrow pointing in the direction of the vector, and how long the vector is gives the magnitude. So in this course, we're going to take the initial point of the vector to always be at the origin, and the terminal point is at the other end of the vector, right? So this is the initial point of the vector at the origin, and the terminal point is going to be at some x and y coordinate located here, where x and y are real numbers. Because we always take the initial point to be at the origin, the terminal point with coordinates x, y will also not only indicate the coordinates of this particular point, but we'll also use the x, y coordinates to represent the vector itself. So this vector v, written algebraically, would just be the pair of coordinates x comma y. Right, so you want to be careful about using the notation in this way, because now, again, the pair of coordinates x, y now represents two different things, right? So both the terminal point and the actual vector itself. So depending on the context that you're working with, it might refer to one or the other, and so it should typically be clear in the situation which one the pair xy refers to, either the terminal point or the actual vector itself. Okay, so in the example at the bottom of this page, you're given two vectors in the plane. Right, so u is the vector -2, -5, and the vector v is the vector 7, -3. So one other thing with the notation is that here, when I denote vectors, I put a little arrow above the letter to denote that the object is representing a vector, right? So it's clear that again, here, when I'm using these coordinates, it's referring to the vector and not just a single point. Okay, so first, the vector -2, -5, right? So that means the terminal point is at those coordinates, right? So -2 is the x, -5 is the y, right? So that's the terminal point, and so the vector itself is an arrow from the origin to the terminal point. Right, so this is my vector u, and then v, so -2 comma -5, and then v is at 7 comma -3, right? So x is 7, and y is -3, so that's there, and the vector is this arrow, so this is the vector v with coordinates 7 comma -3. Okay, so so that's how we represent vectors in the plane, right? So just an arrow from the origin up to the terminal point. So when we're working with vectors, there's two operations associated to vectors. So vector addition and scalar multiplication. Essentially, these two operations are exactly like we do to matrices, right? So you can see here, given two vectors, the way we add them together algebraically is to just add the corresponding coordinates, right? So the x coordinates add together and the y coordinates add together. And the operation for scalar multiplication is, again, follows exactly like we do for matrices, right? So you take a scalar c, so any real number, and if you multiply it by a vector, it's just multiplying all the coordinates by the scalar multiple. So here both the x and y coordinates are being multiplied by c. Okay, so those are the two operations we do for vectors, and they also have a representation geometrically, right? So for vector addition, if you draw in the two vectors that you're adding, so in this example I've drawn them both in the first quadrant, but they don't necessarily have to both be in the first quadrant. They can be anywhere, and it still follows this principle. So it's called the parallelogram law, right? So the two vectors that you're adding form two sides of the parallelogram, right? So then if you draw in a copy of the vector u over here and a copy of the vector v over here, it forms a parallelogram. And so the sum u plus v is just the diagonal of the parallelogram. And then similarly, scalar multiplication, you can view it geometrically as just stretching or reversing the vector depending on whether c is positive or negative. Right, so if c is positive, then that means the scalar multiple scales the vector by the factor of c, right? So if c is bigger than 1, the vector gets bigger. If c is smaller than 1, the vector v gets smaller. And then if c is negative, then the scalar multiple points in the opposite direction. And if c is 0, then 0 times v is just the 0 vector. Which is just is identified with the origin. Okay, so again, the two operations are vector addition and scalar multiplication, and you calculate them in the obvious way, and you can combine them. Right, so in this example below here, you're given two vectors u and v with these coordinates, and you want to calculate 3 times v minus 1/2 times u. So to calculate them, right, so 3 times v, so v is this vector, right, so minus 3 comma 1, then minus 1/2 times u, which is the vector 2 comma 6. Right, so do the scalar multiple first, right? So this becomes -9 comma 3, and then plus, and then -1/2 times 2 is -1, and then -1/2 times 6 is -3. And then now we do the vector addition by adding the corresponding coordinates. Right, so -9 plus -1 is -10. 3 plus -3 cancels out, so that's 0. Okay, so I've done the calculation step by step by first doing each of these scalar multiplication and then finally adding the resulting vectors together. But it's not too difficult to just do all the calculation at once, right? So the first one is just 3 times -3 minus 1/2 times 2, which is -9 minus 1 gives you -10. And then 3 times 1 is 3. Minus 1/2 times 6 is -3, so 3 minus 3 gives you 0. Okay, so that's how we do the calculation. On this last page, we discussed vectors in Rn, and so whatever we did in R2, we can extend to higher dimensional spaces. So it's a little bit harder to visualize things, but algebraically everything carries over in the way you expect them to, right? So in n-dimensional space, right, so Rn, now we represent vectors by ordered n tuples. And instead of using different letters for all the coordinates, because you might have many different coordinates, we use the subscript notation, right? So the vector x has coordinates x1 in the first coordinate, x2 in the second coordinate, x3 in the third coordinate, and so on, right? So there's n coordinates that describe the vector, and depending on the situation, sometimes it's going to be convenient to represent the vector as a row matrix or as a column matrix, right? So here this is a 1 by n matrix, and here this is an n by 1 matrix. But again, you just put the entries of the matrices as the n coordinates of the vector, and you can think of them as essentially being the same. So the scalar multiplication for n-dimensional vectors are exactly how you expect them to be, right? So to add two vectors, you just add the corresponding coordinates for each of the coordinates, right? So add the first coordinates together, add the second coordinates together, and so on. And scalar multiplication just means you multiply all of the coordinates by the scalar multiple. So if you just think of it as a row vector like this, it's exactly the same as the operations for matrices. Okay, so let's do the calculation in these examples, right? So here I'm asked you to calculate u plus 2v, right? So u is 1, -1, 0, 3, and then plus 2 times 0, 3, 2, -1. Right, so if I do this one stays the same. Then I do the scalar multiple, so 2 times 0 is 0, 2 times 3 is 6, 2 times 2 is 4, 2 times -1 is -2. And then I just add the corresponding coordinates together, right? So 1 plus 0 is 1, -1 plus 6 is 5, 0 plus 4 is 4, and then 3 plus -2 is 1. And similar here, I have a separate calculation. So let's write it out. So 3 times v. So 3 times v is this vector. So 0, 3, 2, -1. And minus 4 times u, which is this vector. So 1, -1, 0, 3. Right, so as I said before, it's not too difficult to just do the calculation all at once, but let me just do it step by step. Right, so 3 times 0 is 0, 3 times 3 is 9, 3 times 2 is 6, 3 times -1 is -3, and then -4 times this, so it's -4, -4 times -1 is +4, -4 times 0 is 0, -4 times 3 is -12, then now I add them together, so 0 plus -4 is -4, 9 plus 4 is 13, 6 plus 0 is 6, and then -3 plus -12 is -15. Okay, so again, in Rn, the operations of vector addition and scale multiplication follow essentially the same way.